In the previous class, we learned about basic hardware convention and then how to build a real hardware with hardware description language. So I hope, actually, I expect that every student took the digital logic design course, because this course is the hardware course about the computer system. So if you know about the hardware design and then some basic concept in hardware design, so actually digital hardware design. So I believe you can understand but so I can use the wireless mic now. So until now, so we learned about some instruction set architecture. So it means that we learned about how to organize computer instructions, and then so this concept is very important. So as I mentioned again and again, so instructions are given to computer hardware called processors, and then the instructions change the state of computer hardware. And then, so actually we define the result of the instructions, and then I explained that instructions change the data. The data inside of register files and main memory. So also in the hardware design, so actually in the instruction design, we do not consider about the delay of instructions. That is the execution time of the instructions, because this execution time of the instructions is relative to performance of computer hardware. So actually the computer hardware designer focus on delay. So that is the delta T in this processor. And then, so in the previous class, we briefly covered some basic concept of the hardware design, that is the hardware design. So firstly, we learned about the combinational logic. So you can understand the combinational logic, such as the so input is given to the processor, not combinational logic, and then the output. So output is generated based on the only input data, input signals. That is the definition of combinational logic. Okay, and then also we learned about the sequential logic. So sequential logic means that the sequential logic generates the output of this logic using input signals and states. So states means that it's the stored data actually. So which means that sequential logic has the memory component. So which means the state. States can be defined by some output signals, but these output signals are stored in the sequential logic, and sequential logic generates the output based on the input signals and states. But you can understand some basic data design like this. So there are two state elements called the flip-flops. Actually, we frequently use flip-flops for this state element. And then between these two state elements, there is combinational logic like this. And then the clock is given to the state element. So input signals for combinational logic are sampled by this rising edge of the clock signal, and the combinational logic generates the output from the input signals. But we need to know that these out, so we require, so these outputs are generated at some delay. And the output signals of this combinational logic are sampled by another state element here at the rising edge of the clock signal. So, which means the output of the combinational logic should be generated before this rising edge of the clock signal. Okay, if not, then this digital hardware will generate incorrect result. Okay, that's why this concept is very important for the hardware design. Okay. So I showed some examples of combinational logic and sequential logics here. Okay, and then branch is so okay, so we'll take the piece in this class. But I also update some slides for the today's class. So I update the slide. So and then I also posted this updated slide on the Blackboard and Piazza, so you can download the update slide. So and then the next class for 2 weeks we will provide only online classes. So as I announced it, so because that is the this college's policy. So during the midterm exam period, so we don't have enough classroom actually, so we need to provide the online classes only. And then, as I announced on the Blackboard, we will take the midterm exam on May 2nd, right? So Monday. Okay. So and then this exam is the on-site exam. So you need to show up in this classroom. Okay. Then the exam will be closed for the exam. Okay. So, and then let's see how I also explain about the required steps for executing instructions. So we require 5 basic steps called instruction fetch, instruction decoding, execution, memory staging, and write flag. And then in order to build these stages in computer processor, then we need to also build the hardware components, okay, like this. Also, I explained which operation is required for each stage. So for example, in the instruction fetch stage, we need to read instructions from instruction memory. So which means that we need the hardware components that performs required operations. So in this class, we will we explore some hardware design for each stage in more detail. Okay. So the topic of the today's class is building a data path. So if you see this topic, so this the name of today's topic, then you need to understand the terminology data path. So what is data path? So you can see the next slide. So the definition of a data path is this. So data path means element that process data and address. And then simply we can say that data path is just a hardware component. So actually, why do we build hardware logic or hardware components? So the hardware components look like this. So hardware components receive digital signals and then process these input digital signals and then generate output. Okay? So it's actually same to the definition of a data path. So what is data path? What is a data path? So data paths are elements that process data. So it's data. That's input data. So input is given to the digital logic, and then also addresses are also kind of data which are given to this digital logic. Okay, so data and addresses are actually digital data, and then these digital data are given to the digital building blocks, and then these digital building blocks generate output. So we can say that a database is just a hardware component that process digital signals. And then in the processor, so we can find several database elements. So for example, we can find the registers. So what is the some purpose of registers? So it means that what is the function of registers?
Save data.
Okay, right. So we can save the operand data in registers. Also, we can read and write our data to the register file, and so we can read data from the register file. Also, ALU. So ALU is called the arithmetic and logic unit. So also I'll explain about the ALU. So there are many boxes. So I already explained about some behavioral model of the multiplexer. It's called MUX here. So we can select the input signals. So with the multiplexer, we can select one output signal from some several input signals, and then the selection is determined by select signals. Okay. Okay. So also we can say that memories like instruction memory and data memory are also kind of data paths. So in order to build the entire process, we need several digital hardware components called data path, and then each data path has input ports and then output ports, because so these data path elements receive the input signals via input port, also generate the output signals via output ports. So then how can we build the entire system like processor? We just arrange several data path elements, and then we can connect the input and output port of these data path elements. Then we can build the entire block. Okay? So like this. So as I explained, these rectangular elements. So these elements are data paths, like this PC register, instruction memory, register file, ALU, and data memory, and the multiplexers. Oh, this is adder. Sorry. So these are data path elements. And then as you can see, these data path elements are connected to each other via input and output ports here. So I'm showing how to build some complex systems. So first, we define the operation of a very simple data path element. So for example, we can define the operation of a very simple instruction memory. Okay, then we can build this data block as data path element. Okay, this is hardware block. So how can we build this block? So also I will provide the design lab, the second design lab. So in the second design lab, you will be requested to build these simple data path elements. So first, we design individual data path elements based on those required operations, and then we connect the input and output ports of data path elements. Okay. Then we can build the entire system like this. It's a processor. Then let's see how to build each step of single cycle processor. So, so in the previous class, I mentioned that in order to execute the instructions, so we require 5 steps. Like, oh, okay. So we require 5 steps called the instruction fetch, instruction decoding, and then execution, memory, and write back. And then let's see which digital components like Datapath elements, and then how the wires are connected to these Datapath elements. So let's see the instruction fetch stage. So these are the Datapath elements that is required for building instruction fetch stage. So what is the required operation of instruction fetch? Oops. Instruction fetch. So we can fetch instructions from instruction memory. Okay, that is the required operation in instruction fetch stage. Then which Datapath elements are required. So in order to fetch instruction, we need to generate the program counter value. So I already explained that program counter is an address for instruction data. Okay, so we need to generate the program counter value. And then with this program counter value, so we can read data from the instruction memory. Then we can get an instruction from this instruction memory. So this is the current program counter value. Then we need to update the program counter value. So usually for the next instruction, it has the program counter value like PC plus 4. So this PC is the current program counter value, and then by adding 4, then we can generate the next PC value. So program counter is updated every cycle. Okay, so which means that actually the clock signal is connected to the program counter, and then at every rising edge of this program clock signal, the program counter value is updated. Okay, so this is the single cycle processor. So definition of the single cycle process is that this processor can execute a single instruction every cycle. Okay, which means that we need to read an instruction every cycle. So which means we need to generate the program counter value for every cycle. So that is the operation of the instruction fetch stage. It's very simple, right? We update the PC value, and then so every rising edge of the clock, that's the rising edge of the clock, the current PC is generated. And then with this current PC value, this PC value is given to the instruction memory, and then we can get an instruction system, instruction fetch. Then how can we build this data path? So let's see the program counter. So I already explained about the behavioral model of the program counter. Okay, so this means that I explained about the operations for program counter. So PC register. So this this is called the program counter register. It's a special purpose register. So program counter value is stored in this PC register. And then next is the operation of the PC register. So this is the 64-bit register because we are learning about the 64-bit computer, okay? But actually, this 64-bit is very large. So we cannot use this very large memory space. And then usually the width of this register is same to the width of the virtual address field. Okay, the virtual address, the width of the virtual address. So usually we are using the 48 bit. I don't know why. Okay. So we are using usually 48 bits for the virtual address. So actually the size of this piece is the same to the size of the virtual address actually. So, but we are learning about the 64-bit computer, so you can think like that. The width of this PC register is also 64-bit. So which means that 64-bit data is stored in this program counter register. And then, so actually this program counter register works like E flip-flop, okay, which means that at the rising edge of the clock, the PC register generates the current program counter value. Okay, so current PC is generated just at the rising edge of the clock because this is the single cycle processor. So this single cycle processor executes a single instruction every cycle. So which means that we need to fetch every instruction for every cycle. Okay. And then, so also this processor need to execute the next instruction, and in order to fetch next instruction from instruction memory, then this next PC should be prepared. Okay. So in this figure, this is the current PC. So current PC is generated from the program counter register, and then the current PC is added by 4, and then so this is the next PC. So which is equivalent to the current PC plus 4, and then we will use this next PC value for the next instruction. Okay, so we are using this current PC value for current instruction, and then we will use next PC value for the next instruction. So which means that in the next cycle, the current PC will be updated to next PC value. Okay, because in the next cycle we will use the next instruction. So you can find some behavioral model of the program counter here. So as you can see, this is the program counter. So we define the 64-bit data for this program counter. This is PC under the curve. So which means current program counter. And then I already explained that the operation of the program counter is very similar to D flip-flop. So as you can see, this is the arrays statement for D flip-flop. So arrays underbar FI. So if we use the arrays underbar FI, then we can build actually flip-flop. So D flip-flop actually. So we can find the sensitivity list here. So at the rising edge of the clock, so positive edge, and then also this flip-flop has the asynchronous negative reset. Okay, here. So the reset signal is actually very important for the data system because the reset means that the computer system is turned off. So which means that any supply voltage is not given to our computer system. So in this case, the computer, and then if the power is on, then computer systems may have a very unexpected state. So unexpected data. So which means that the states in this computer system can be very unstable because there are unexpected data in the computer system. So, and in order to avoid this situation, we need some reset signal. And then, so in the reset signal is given to the processor, and every state in the computer system are initialized. Okay. And then it's the same to the PC. If the PC does not have any reset signal, then PC will have a very unexpected value. Like, so we cannot expect any data into this program counter. So maybe the PC maybe have the very some unstable value. So we need a reset signal for the program counter register. So when the reset signal is given to this program counter, so we initialize the program counter value as all zeros here, and then if the reset signal is given to the this program counter, then program counter value is updated to the next program counter. Okay. So this behavioral model represents this hardware model of the program counter. Okay. So what does it mean? The PC curve is updated by actually next PC when the wiring edge of the clock. So this should be PC underbar curve plus 4. Okay, because this is the next PC. Do you understand? This is the behavioral model of program counter. Okay, and then if we use this behavioral model in our audio description language, then we can generate the audio components like this. Actually, this part. So we can build this part, so program counter part. Then let's see how we can build instruction memory. So first, you need to know the definition of memory component. What is the definition of memory component? What is the definition? So we can store, we can store any data in memory components. And how can we access this data? Actually, the memory component has many rooms actually, many rooms for our data. And then we can access this data with address, because these rooms in memory components can be indexed by address. Okay, that is the definition of memory components in the control system. So then, how can we build behavioral model of the instruction memory? So if we see the instruction memory here, we can find that instruction memory has the input port for the read address. Okay. Also, we can find that instruction memory has the output ports here, and we can get instruction from this output port of instruction memory. So instruction memory has received the address But we can say that address is the program counter value. So which means that the program counter is given to the instruction memory, and then with this address, we can access the instruction stored in this instruction memory. Okay, so let's so then what is the behavior model of the instruction memory? So I already explained that the memory. The memory is the data array. The data array indexed by an address. Okay. Then how can we define this behavior model of the instruction memory? So we can use the address using the current PC value M1. Sorry. And then the data is the on element. So on element, the data element indexed by PC. Then we can build the behavior model of the instruction memory like this. So as you can see, we define some array. So it's called the data array. And then this is the width of a single data array element. Okay. So you know the size of a single instruction of RISC-V is 32 bit, which means that the size of the single data array element is 32 bit. So 31 down to 0. And then in this example, we assume that there are 256 elements in this instruction memory. So this is the data element. And what is the POut? So the required operation of instruction memory is that we need to read data, then indexed by address. Then what is this value? So we can store our instructions in the element of this data array. So there are 256 data array elements here. Then how can you access a certain instruction? What is this value? Data indexed by address, which should be data indexed by some address. Okay. So that is the behavioral model of memory. With this address, we can read the data. So we can select a certain data element from the data array in the memory component. Then we can get the receive. This value it becomes the output of the instruction memory. Okay. Okay, that's me. So this is the behavioral model of the instruction memory, and we already defined the. We can build the program counter like this, and then by connecting program counter register and the instruction memory here, then we can build the instruction fetch stage. Okay, understand? And then let's see the instruction decoding and execution stage. Okay, instruction decoding and execution. So in the instruction decoding stage, the instruction from instruction fetch stage is decoded. So decoded means that the computer processor recognizes which instruction is given to this processor for a certain clock cycle. So first we need to decode the instruction. Then how can we decode the instructions? And actually in chapter 2, you learn how to encode instructions. Okay, so which means that like add x1, x2, x3. So this is the RISC-V assembly instruction. And then encoding means that this instruction is represented using digital data, like 32-bit digital data, the digital instruction. Okay, and then decoding process is the inverse of this process actually. So in the 32-bit data, so 32-bit instruction, by decoding some field of this 32-bit data, we can recognize which instruction is given to a processor, right? So it's an inverse process of the encoding, okay? So by decoding this instruction, then we can recognize the instruction. And then for the archive instructions, the archive instruction like add x1, x2, x3, then we need to first recognize the kind of instruction, like add instruction. And for the archive instruction, then we need to recognize the source register numbers and destination register number, right? So because in the archive instruction, we need to access register file with the two source register numbers like RS1 and RS2, and we need to define the destination register number RD. So, and then if we recognize the RS1, RS2, and then RD, destination register number, then we can access the registers. Okay, so it's a register file. So, in order to support the arithmetic instruction, the registers need to receive two source register numbers, okay, and then also registers need to receive one destination register number. So you can, as you can see, these registers have two sources, read register 1 and read register 2, and then the width of this port is the 5-bit, okay, 5-bit and 5-bit. Also, registers receive write register number here for the RD, and then also the width of this write register is also 5-bit, because there are 32-bit general purpose registers in the RISC-V, right? And which means if RISC-V has only 16 registers, then the width of this read register should be 4, right? Okay, and then in order to write the data, so we need the write data port. And what is the width of this write data? 64 byte, because we are learning about the 64-bit computer system. So which means that the width of the single register is also 64-bit. So which means this data width is also 64-bit. Which means also read data port has the data output, and then the width of these data outputs are 64-bit. And then the registers, so new data can be written to the register file or not. So for example, if we use the load instructions or archive instructions like add or exclusive or arithmetic instructions, then we need to update the registers. But if we use the other instructions such as branch instructions or store instructions, we don't need to write data to register file. So which means some instructions need to write data to the register file, but some other instructions do not need to write data to the register file. So we need to control these different situations. Okay? So which means register require control signal for register write. So we call this control signal as read write. So which means if read write is 1, so which means that the registers are written with this new write data. But if not, the registers are not updated. Okay. And then, okay. So this is the R-type format. And then as I explained, with the decoding process is the inverse process of the encoding, and then by decoding 32-bit instruction field, and we can recognize these instructions, these data. Okay. Then let's see the behavioral model of the register file. So we already learned about the memory component and instruction memory. So, and then it's very similar to the register file, because as you know, so if we see the register files, there are 32-bit general purpose registers, so which is simply register array of registers. Okay, and then we can access each element of a register file using register file number, the register number. Okay, so if you see the this RF data array, so it's some registers in the register file. So you know the width of a single register file is 64-bit, and then we have how many elements? 32, right? Because there are 32 general purpose registers. So this should be 0 to 31. So then how can we access the register? Okay, so we can access, and then as I explained, the register files support the 2 register bits with the source registers, and then 1 register write. And then this register write is controlled by read-write signal. So we can distinguish the write operation here and the read operation here. And then let's see first. Let's see read operation first. Then how can we access the register data here? Simply like this instruction memory. So we can access the instructions. So it's actually a certain data element with the address, and it's the same to the register file. So the registers are indexed by register number. So which means we can also access a certain register with the register file number RS1. Like this. This is the read data one, is data for the source register number 1, and we can access the data like this. Oh, is this correct? Is this correct? It's not correct because I'm asking. So why is that? So actually, we already learned that x0 has always 0 values. Okay, which means if the RS1 equal 0, then the read data 1 should be 0, right? Okay. And then if not, it should be RF underbar data indexed by RS1. Okay, so we need to consider this special case. Okay. And then how about the write operation? Write operation is enabled by read-write signal. And then as you can see, actually we cannot find any clock signal here, but you know, this type process of design, the write of the register, write to register should be sampled by clock signal. If not, we will generate the infinite loop in the register file. So which means think like this. And oops, x1, x1, x1. So what does that mean? By reading the same data from the register x1, and we perform the x1 plus x1, and then store this result to the also the same register file. And then you know in this processor, this instruction is possible, right? So we can use this instruction. But if we do not use this clock signal in the register file, then what will happen? So this update is continuously update to the x1 again and again, so infinitely. Then this value should will have a very large value. But it's an infinite loop, so we cannot control this loop. Okay, so that's why the register file should be sampled by the clock signal. So as you can see, this is the write operation. The write operation should be sampled by clock signal only, and then write operation is enabled only if the value write is 1. Okay, if not, this write operation is not performed. And what should we do here? So new data is updated to a certain register file, so it should be on the data indexed by which register number? Destination register number. It is updated by new data. Should be right data. Okay, this is the behavioral model of the register file. Okay. And then the register file operates like actually the memory component. So let's see. And then ALU. So we use the ALU for the execution stage. Okay, execution stage, and then the operation of the execution stage. So in the execution stage is ALU receive the 2 operands, and then we can, so the ALU can receive 2 operands from register file, or we can use immediate data. Anyway, the ALU receives 2 input operands, and then do something defined by instruction. For example, for the add instruction, the ALU performs add operation and then generate the result. Okay, ALU result. Okay, so we can build the ALU based on this definition. And then we will learn about the ALU in more detail in the next class. Okay, but as you can see, we can build the ALU like ALU receive the 2 input operand and then generate the output data. Okay. Then, before explain about this memory stage, let's take the piece. So, it's 2. I will give you 3 minutes. I will give you a forming for start taking this piece. This is very simple. And then I also generate the copies on the blackboard, and you can submit your answer via blackboard. Okay. So I will give it just a screen. let's go back to the class. I explained until the execution stage, and maybe I also explained about the memory stage. Okay, so memory stage, and then actually two instructions like load instruction and then store instructions only access the data memory. So which means that with the load instruction we can read data from the main memory, and actually it's a data memory. And then with the store instruction, we store data to this memory. So this is also memory, it's a data memory. So which means that this memory is also it's similar to the instruction memory or register file. But there are two different directions. There are two different operations like read operations and write operation. So we require read operation for load instruction, and then we require write operation for store instruction. Okay. So which means that the data memory also require control signals. So like register file. So which means we can read data from the data memory. So which means we may require memory read control signal. Also, we need to write data to the data memory, and then for this operation, so we require memory write control signal. So then you may ask that, like, also we need read operation and write operations for the register file. But as you know, the register file has only read write control signal. We cannot find any control signal for register read. But in the memory design, we can find two control signals like memory write and memory read. Why? Why is different? Why do we need the memory read signal and the memory write? And then as you can expect, memory write is enabled if the memory write signal is 1, and then it's the same to the memory read operation. If memory read is 1, then this data memory performs the memory read operation. Then why do we need the memory read?
추측인데 CPU랑 속도가 달라서 그거를 맞추기 위해서 어떤 제약이 좀 있는 게 아니라 레지스터는 클럭 속도 바로 반응이 되기 때문에 그냥 불러오셔도 되는데 용량의 속도가 달라서 그냥 추측. 네.
But this is the single cycle process of design, which means that every operation should be completed within one cycle. So which means you know the delay of the register file should be much shorter than the clock period. So and just actually it's the same to this data memory. So data memory access time should be shorter than the clock period time. So the reason is that actually, if we see the instruction, then every instruction needs to read data from register file. Right. So every instruction, like add instruction, store, load, and also branch instruction like BQ. If you see these instructions, actually these instructions, every instruction accesses register file for read operation. So which means the read, if we take some control signals, read should be always 1 for every instruction. So we don't need to actually make this control signal. But data memory is a little bit different. So for the read operation, we just load instruction requires the memory read operation, and then also So this store instruction just require the memory write operation. So which means, but it's not harmful if the memory data memory generates some any data from this read data port, then it's not harmful for the processor. But if we just consider some power consumption of this data memory, so which means that if we do not have a memory read or control signal for this data memory, then this data memory need to work for every address input. And then if you see the some connections here, actually the output of ALU is connected to the address port of the data memory. So it means whenever the ALU generates the output, then this address value is changed. And then if the address changes, address is given to the data memory, and data memory need to work for the new data out. So it's kind of a waste of power. Okay. So, but this is not harmful for the result of this single cycle processor. But if we just consider some required operation for this data read, so and then not to save the power consumption, then we can make the memory read control signal. And then memory read operation is performed only if this memory read is 1. Okay. And then also it's same for the memory write. So only store instruction requires the memory write operation. So this is the control signal for the memory write. Also, I already explained that we also the RISC-V instruction also uses immediate data. Okay, so if you see the loop instruction, X was store instruction, and then in order to generate the address, so we use the immediate data. So which means, and then as you can see here, the data memory received the address from the ALU. So which means that ALU generate the address for load or store. Because in order to generate the address for data memory, then you need to perform like here, and then this is offset. Then we need to perform the RS plus offset. So this is the add operation. So which means we need to generate the immediate value from the instruction. So the load and store instruction, the immediate value is included in this instruction, and then actually the size of the immediate value is the 12-bit. But what's different? If you see that this ALU need to receive the 64-bit data. Okay, so then which means that we need to extend the length of this immediate data to the 64-bit. Okay, so this is the immediate generator. The immediate generator receives the 12-bit immediate value from the instruction, and then the size of the instruction is equal to bit, and you can see that the input of the immediate generator is the 32-bit. But we already know that only the 12-bit immediate data is stored in the instruction, and then we need to expand the width of this immediate value to the 64-bit in order to use the ALU. And then also you need to remember that the MSB of the immediate value is the sign bit. So which means that we need to perform sign extension, right? So I will show So this is the I format instruction. As you can see, I format instruction includes the immediate data. It's a 12-bit, and we need to remember that this is the 2's complement signed number. So you need to perform sign extension. Okay, so let's see the behavioral model of the data memory. Okay. So actually, this behavioral model of the data memory is also similar to the other type of memory, instruction memory or register file. So you can find the array of the data array here, and then this is the set actually. It should be 63 because we are running about 64-bit computer also. So if you see the this single cycle processor architecture here, then the data, this data memory receives the input data from the register. Okay, and then the width of this register data is the 64-bit. It should be 64. Okay. It should be 63 because the width of the single data is the 64-bit. Then let us assume that this data memory has the 256 elements here. And then also we can define the write operation and then read operation like here. So read data is controlled by memory read control signal like here. And then based on this memory read control signal, then read data may have any value actually, but maybe 0. And then if the memory read is 1, then we need to access a certain element from the data memory. So this should be data indexed by otherwise is 0. Okay. And then so memory write is also very similar to the register file. So we can, if the memory write is 1, then a certain data indexed by address is updated by input. Okay. So this is the behavioral model of the data memory. I believe you can understand. Okay.
And write the 맨 위드랑 변수 if 조건을 대면 좀 다른 형태인 것 같은데 왜 그런지.
이거랑 뭐야?
네.
이거랑 똑같아요 사실. 우리가 이제 if 문제 때 if a equal 뭐 1 이렇게 쓸 수도 있고 사실은 이렇게 쓸 수 있죠. 그러니까는 뭐 a 같은 경우 C에서는
값이
모든 값을 이렇게 쓸 수 있잖아요. a 아니면 이제 true가 됩니다. 쓸 수도 있고 사실 이거 똑같이 이렇게 쓸 수도 있잖아요. 이거랑 이것도 베릴로그에서 똑같아요. 그러니까는 이렇게 쓸 수도 있고 어차피 근데 빅데이터는 1 아니면 0니까는 이렇게 쓸 수도 있고 이렇게 쓸 수도 있어요. 똑같은 거예요. C에서도 그 두 개가 가능한 것처럼 베릴로그도 두 개가 가능합니다. And then we need to consider the branch instruction. So the operation of the branch instruction a little bit different from other instructions. So what is the operation of the branch instruction like BQ, RS1, RS2, and target? So if we see this BQ instruction, the BQ first read data from the register file by source register numbers, and then performs tests the equality of these two operand, so we need to check the equality. And how can you check the equality? You can just perform the subtraction, like RS1 minus RS2 is 0. So we need to check the 0 of this subtraction. And then if the value is 0, which means that RS1 is equal to RS2, then the PC is updated by current PC. So actually, the next PC, so the next PC is updated by current PC plus target. Target is left shift by 1. Okay? So actually it is target multiplied by 2. So this is the required operation for BQ. And then with this data path element, then we can build up some data path element and then control signals for this branch instruction. Then, so I already explained the required operation for branch instruction. The first, we need to read data from the registers. So which means that the RS1 and the RS2 are connected to the input ports of the registers. Also, in order to generate the target of the branch instruction, then we need to extract the immediate value here. So which means that we need to use the immediate generator, and then with this immediate generator, and then is generate the 64-bit data, and then this we need to perform the add operation. But problem is that we also need to check the equality of two operands from register file. Okay, so we need the add operation for calculating target of the branch. Also, we need to perform subtraction for checking equality of two operands. Right. So actually, for this equality check, then we can use the ALU, because ALU can just performs any arithmetic operations. But for this target generation, then we need to use another adder. So which means for branching operation, then we require additional adder here. Okay, so with this adder, so immediate value is shifted left by 1, shifted left by 1, and then using this adder, the current PC is added with this immediate value, and then generate the target of the branch instruction. And then this target of the branch instruction is updated to the actually PC. If branch is true, right? Okay. This is the operation of branch instruction. Then how can you this is so if you see the this full data path of the single cycle processor, then you can find the some required data path and then some wires, which means the connections for branch instruction. Okay. Oops. So as you can see, so for the branch instruction, the register files are accessed and then immediate with the immediate generator, the immediate value is generated from the branch instruction. And then we need to perform the shift left. So you know this is the PC under the curve. So the input of this adder is the PC number current PC. So current PC is added with this shifted immediate value. Then this is the current PC number by branch. And then I explained that we use this target PC only if branch is true. The condition of the branch is true, which means if there should be mux here. So which means based on the condition of the branch, the next PC, the next program counter value can be PC plus 4, PC current plus 4 here. So this is the PC current plus 4, or the target PC by branch. Target PC by branch. So we need to select based on the condition of the branch instruction. So here we can find the PC source selection signal for this multiplexer, and then this output is the PC next. Okay, and then now the PC is sent to the right proximity. So this is the data path and wires for branch operation. Okay. So now I covered some required steps for executing instructions. Also, I explained about the data path elements for each stage here. Okay, so I explained about some required data path and then control signals for branch instruction. And then if these are merged, then we can build a single cycle processor which look like this. Okay, so everything is merged and then every data path is arranged or assigned, and then the input and output ports of the data path elements are connected for supporting every instruction. Okay, and then we can build a single cycle processor like this. Okay, so please remember that what I covered in this today's class. Okay, so I start from the very simple each data path element, and then we can build the single data path element, and then also we can define the operation for this data path element. And then we define the input and output ports. Then these input and output ports are connected each other. Then we can build the bigger system, so processor. Okay. Okay. So I will stop here. Then the next class, the online class will be provided. Please remember that. So do not come here for the next class. Okay. Thank you for your attention. And then if you have any question, you can ask any question. Okay. Thank you guys.